Oh no, we did say it matters. So we're on the third lesson. Oh right, okay. I didn't realise that that's already on the third lesson. Can you see okay? It's not too bright. You can see? Yeah? Okay. So next lesson is kinetic theory. Okay. Got this? Yeah? So we've talked, we have, we've talked about pressure in mechanics. And pressure means how much something is pushing on something else, basically. So as a formula, pressure, force over area. And of course the units are pascals, and I probably gave you the definition of a pascal already, but 1 pascal is 1 newton per 1 meter squared. So I don't think you have to write this down because you already have this. Okay. So the way we're going to think about our ideal gas. Okay, well actually let me turn the light off, it's a bit bright. Have you done ideal gases with Lorraine? Ideal gas, have you done that with Lorraine? Do you know what it means, ideal gas? Our noble gases, ideal gases. Noble gases are like helium. What else? I think they might be. I think they might be ideal gases. Ideal gases are just gases that we make some assumptions about the gas, and these assumptions we make about the gas, we say that the gas is ideal if these assumptions are reasonable for the gas. So the assumptions are it's a low density. So the first thing for a gas to be ideal is it needs to have a low density. Second thing, it's colliding particles. So we picture our gas as being lots of little particles just colliding with no attraction between them. My goodness. Yeah. Do you know what I mean by no attraction between them? There's no force pulling the particles together, and we don't consider gravity. Yeah? So they're just balls bouncing around in a box with no gravity. That's basically the idea. So I have a picture here. Oops. So we picture our gas as just being particles just bouncing around, and that's all that's happening. Nothing special. And we can try and get some formula for this situation. Okay. If I can remember how to prove it. So let's have a look at the proof. Huh? Kind of actually for the exam, because the exam won't ask you to prove the whole thing, but they may ask you to comment on parts of the proof. So, for example, maybe I think 3 or 4 years ago, one of the questions was, what are the assumptions in an ideal gas, you know, or another one was describe the ideal gas for the proof, you know. So you don't need to have the full proof, but it's just good to see so you can understand it and talk about it. Okay, can we do the proof now? Let's have a look. So, firstly, to make things easy, we'll put our gas, like in the picture, in the box. And also to make it easy, we imagine that the gas is full of these balls, which are the particles, and we'll call each side here L. First thing, okay? And I'm interested to see what happens when a particle hits the wall of the box. Okay, so if I zoom in, here's the wall of the box. And here's a particle here. And we'll say that all the particles have mass m, or all the molecules have mass m, and their speeds can be different. Some can be going fast, some can be going slow, but we'll say that on average its speed is u. And it comes along, hits the wall, and then bounces back. Got that? Yeah? So, let's have a look at what's happening here. There's going to be a change in momentum, because before it hits the wall, its momentum is mu. And then what's its momentum after it hits the wall? What do you think? No, not zero. Because it hits the wall and comes back. So the momentum will be minus mu afterwards. Yeah? So its total momentum will be 2 mu. Total change in momentum. Okay. So far, is that okay? Yeah. Now, if I divide both sides by delta t, the time here, what will this become? The force. So you have force now equals 2 mu over delta t. But remember, pressure is force over area. So force is pressure times area. So here I can get pressure times area equals 2 mu over delta t. Is that okay so far? Yeah. Now, the area, what's the area here?
2L.
No, not 2L.
1L.
Oh, no, you were closer to 2L.
L.
Thank you, yeah. L squared. So now we can get PL squared equals 2 mu over delta t. So I'd like to try and replace the delta t now. So we can use our distance speed time triangle. What is time equal to? Yeah, distance over speed. Yeah? Now, let me just, right here. Well, we know the speed. Now, what's the distance here? Yeah, what is the distance here? What letter? Yeah, we have to be a little bit careful because it's not always clear. But if we imagine the particle starts here and it's going to the right, I mean, where should we draw the particle? We don't know where it is because it could be anywhere. So we'll just draw it in the middle. On average, it'll be in the middle. So it'll come along. It'll hit the wall. And then we'll come back, hit this wall, and then come back. So I think I've gone too far. Hits the wall, that's L over 2. and then it comes back to where it was at the start. That's L over 2. So I think we'll go with L. It has to travel there and back. L over 2 and L over 2. So I think I'll go with L over 2. So that would be L over 2. So now I have PL squared equals 2mu over L over 2u. So I have PL squared equals 4mu squared over L. So I just brought this 2u up to the top here. Now I can bring this L up to the right. So now I get PL cubed equals 4mu squared. Now what's L cubed?
The area.
Not area.
Volume.
Volume, yeah. So now you get PV equals 4mu squared. Couple of small changes, or something else to consider. So in our picture, we imagine that the particle was traveling in one dimension, just goes to the wall and comes back. But in reality, it's traveling in 3 dimensions. So if I imagine it traveling in 3 dimensions with speed u, it has 3 components. One this way, one this way, and one this way. On average, each of these will be the same speed. And you might say, why? Well, if on average this one was bigger than these two, it would mean the gas is on average rising. Likewise, if this one was bigger, it would mean the gas would be moving to the right. So to keep it all kind of balanced and symmetric, we say that each speed is the same in each direction on average. So maybe some particles will have a lot of speed this way and nothing here, and then other particles would have a lot this way and maybe nothing here, just on average. Do you understand? So using Pythagoras, we can say x squared plus x squared plus x squared equals u squared. So 3x squared equals u squared. So x squared equals 1 over 3 u squared. So to go from 1 dimension to 3 dimensions, I just need to take my u squared and divide it by 3. So if I go back to here, I need to put a over 3 here. And now I'm starting to wonder about this L over 2 business, if it's, or this L. I don't know if it should be 2L. Do you know, I think it's 2L, because when the particle gets back to the start, it isn't really at the start because it's heading the wrong way. You have to wait until it comes all the way back around before it's back at the start. I think I'm going to change it to 2L. So if I put a 2 here, they'll cancel. So that should just be a 2. Yeah, okay, this feels better. I felt my answer was a little too big. Okay, next, what I'm going to do is take 4 over 3 out and put in here a half mu squared. So, because 4 over 2 is still 2. The reason I did that is, what's a half mu squared? Yeah, so now you have, oh, and L cubed we said was volume. So now I have PV equals 4 over 3 KE. Now that's the kinetic energy for one particle. And that's the, this is like the situation for one particle. If you don't want it for one particle, if you want it for all the particles, you have to make a little bit of a change to it. We'll put, yeah. Hang on. So PV. My head. I'm too tired. I didn't have my coffee yet. Yeah. That's only for one particle. For the whole thing, I'd have to add the kinetic energy up for all of them. So really, PV is 4/3 times total kinetic energy. Yeah? If I divide both sides by n, the number of particles that I have, then I get PV equals PV over n equals 4/3, and then what's total kinetic energy divided by n? Average kinetic energy, total divided by n. So I'll just write AKE. So then I can finish by writing PV equals 4/3 times n, and often average kinetic energy is written like this. Kinetic energy in these brackets here. I might have said this before actually. So I'm not 100% sure about the n. I hope I wrote the formula down on the next slide. Okay, actually I guess I kept my formula in this form rather than dividing it by n, so I'll just branch off here. PV is 4/3, and this is the total energy. You add up all the kinetic energies. I didn't bother writing it like this, so we'll just not look at that. Okay, and this is our formula here, which is, oh no!
Okay, so PV equals 4 mu squared, is supposed to be 2 mu squared, and then everything else 2/3.
Oh, you're right. 2 here.
Yeah, and then the next one.
That's 4/2 to make the 2. That's 4/. Hey, I've lost a 2 somewhere, didn't I? Oh, okay. I lost a 2 somewhere here. I should have gotten 2/3, not 4/3. That's life. If I didn't change this to 2, if I kept it as what did I want to keep this as L, wasn't it? So the 2's wouldn't cancel here. So there's be 4, but it'd be bigger. This would be 8. So it's like I missed a 2 somewhere down here with the T. Maybe I was wrong. Maybe I should have gone with from here to here. I should have used this distance, L/2. Then that would fix it. Oh well. You don't need the proof for the exam. You just need to understand what the concept was. So the concept was we calculate change in momentum to calculate the force, to calculate the pressure, to eventually end up with this formula. So this is the one you need. The total kinetic energy, yeah.
Total?
Yeah. Total. You know, I feel like that must have been it. I should have used L over 2. If it was L over 2, then that's a 4. No, look. 2mu over L over 2. Why is this a 2u?
This is the
Oh, that was the L over 2.
This is the
Oh, I wrote my 2's in the wrong place. I think that was the problem. Let me just take it from here. 2mu over. Oh my goodness. Yeah, this is my mistake. It was to be 2L, but my mistake was I should have deleted this 2. I should have had 2mu over 2L over u. This was the distance and this was the speed. So it should have been mu squared over L, which then should have been 1/3 mu squared over L when you put in the 3, which then should have been 2 over 3 mu squared, and the L goes, yeah, sorry, that was it. I shouldn't have had the 2 here. So this is the problem. So there's no 2 here. So there's no 2 here. So this is a 2, and this is a 2. So this is a 2. You add them all up to get the total. Rats. This is what happens when I don't have coffee. This is what happens. Okay, have you got the result taken down? Now, what makes this result interesting? Well, maybe you can tell me. What makes this result interesting?
Can you get the pressure of the volume?
That's not interesting. Anybody can do that. You just need a meter stick. By the way, someone stole my meter stick. Do you know that? Somebody stole my meter stick. I have to buy a new one now. I lent it to a teacher and now it's disappeared. Can I borrow your meter stick? I'm like, yeah, sure. Like, where's the meter stick? I don't know. I left it in class. It's gone.
You left it in the class?
No, not me. They left it in the class.
The teacher.
And now it's gone. Okay, what makes this interesting, do you think? Well, is it easy or hard to measure pressure?
Hard.
Why? How do you measure pressure? You can use something like, barometer. Yeah? How do you measure volume? Like, for example, how would I measure the volume of the bin?
Shape.
Huh?
Shape.
Yeah, but how do I measure the volume of the bin? What would I do? Oh, come on. Do you need coffee too? Well, I could measure all the sides.
Yeah.
And then multiply them, yeah. I'm not trying to trick you. So, is it easy or hard to measure volume? It's easy. Pressure? It's easy as well. But what about measuring the energy of each particle? That would be quite hard. Because not only would you have to measure the mass of each particle, but that's going to be actually easy because they're all going to be the same particle. You have to measure the velocity of each particle. Just not possible. So what makes this interesting is that by knowing something easy to find, PV, you're able to know what the total kinetic energy is. So that's what makes this formula interesting enough to have a proof and to know for the exam, that you can go from what you might call the outside day-to-day world and relate it to something on the atomic level. The total energy of each particle times 2/3 is equal to pressure multiplied by the volume. Yeah. All good? Yeah. Okay. Continue? Yes? Now, next, another formula, I'm afraid. We'll consider the pressure on a sphere submerged in a liquid, and from this we should find a formula for pressure in terms of height. So, just maybe before we do that, probably, no, I'll do the proof first actually, and then we'll talk about atmosphere. Alright, this proof isn't as long. So we imagine we have a liquid, and we have an object in the liquid, and it's a distance h down from the top. And we'll say that this is a radius of r, and this liquid has density ρ. Okay? If you look at this, you have, well, okay, let me try and draw this for you. You have some force being pushed onto the liquid. This is from the water, like pushing in on it. You know, it might be actually easier if I draw it as a circle rather than a sphere. So I'd imagine a circle here, like a I don't have any coins, like a coin just in the water. So what's pushing on the water? Well, what's kind of happening is the water above it is pushing on the disc. And if this is down further, will this feel more or less force? What do you think? Imagine the disc was further down. Will the force on the face get bigger or smaller? What do you think? It'll get bigger because what's happening is we imagine that all the water that's above the disc is pushing down on it. If this was underwater, what's happening is all the water that's above it is pushing down on it, making a pressure. So if I go lower, why is the force greater? There's more water, yeah. So let's calculate the pressure that it feels. What's the formula for pressure? Force over area. Now we'll make this a circle just to make it a bit easier. What's the formula for area?
Pi r squared.
Yes. And in this case, what did we say the force was? Where's the force from what? From the water's weight. So this force is a weight. What's the formula for weight? mg. Okay, I said water. It doesn't have to be water. It's usually water. We need to find the m. We only know the density. So we can use the formula density is mass over volume. So mass is density by volume. So this will be density volume g over pi r squared. Now, what's the volume? Oh no, that's the density of water. The volume. And it doesn't have to be water. What shape is it? You learned this word this week or last week actually. This shape here. Cylinder, yes. And the formula for volume of the cylinder is pi r squared h. So this would be rho pi r squared hg over pi r squared. Now what's nice here, the pi r squareds cancel, so you're left with pressure equals density times the h times the g. Now what's really interesting is, where's the r in this formula? It's not in the formula. So it doesn't matter how big it is. So if you make the r equal to 0, then you have the pressure at a point. So if you're at this point, what's the pressure? This formula here. So this is our result here. This is pressure. And you can see the pressure increases the further down you go. Also, what else would make the pressure bigger? If you were in a denser material. This is what we need. So I don't think the proof is too bad. I think it's worth writing down. Yep. Continue. Sharif? How did Mir get on yesterday? Haven't seen him. Continue? Yeah. Okay, some more definitions. Have you done one atmospheric pressure with Lorraine? I don't know if this comes up. One atmosphere of pressure is how much pressure is usually in a room at sea level. Now, of course, it changes. When it's summertime and the weather is good, the pressure increases, and then in wintertime it will decrease, but it's roughly around about what we call 1 atmosphere of pressure. And the definition of 1 atmosphere of pressure is it's 101.35 kilopascals. Now, I don't know why I made the K big, this should have been small. Kilopascals.
Pascal?
Yeah, for pressure. This is the pressure on you right now from the air. Pretty big, right? We don't feel it because we're used to it. But believe it or not, there is a lot of pressure from the air on you right now. And it's for the same reason as in the proof, that when I'm sitting here, I have all the air above me pushing down on me. And if you think about it, that's a few kilometers of air pushing down on me. Do you understand? So it's actually a really big, 101 kilopascals. That's 101,000 newtons per meter square. It's a lot. What? Yes. Yes. You just don't know it because it's around you all the time. You know. You only notice pressure when you don't have it anymore. So, like, if all the air suddenly left this room, you would definitely notice it then.
So we move fast.
Expand a little bit. Pop. I don't know. Never tried it. Right. Okay. So here's an interesting question. What is the pressure on you if you're swimming 5 meters below sea level? So let's calculate this one. So you're swimming here, and this is 5 meters below sea level. So the pressure formula is rho GH. What's the density of water? 1,000, 9.81 times 5. What do we get? 49,050. 49.1 kilopascals. Straightforward. Yeah?
How can we make a trick question out of this?
Don't worry, I'm way ahead of you. How thick is the Earth's atmosphere? How's that for you? Tricky enough?
Yeah.
Okay. And that's the last one, so we'll do this one. Right, so the Earth's atmosphere. So here you are on the Earth, and we can think about it as like being under the water. You're in like an ocean of air. Yeah? And this is the H. You're at the bottom of the ocean of air, if that makes sense. So we can use our formula: pressure equals rho GH. Pressure, I gave it to you earlier. Your pressure here is roughly 1 atmosphere, which is 101.35 kilo. That's equal to rho GH. So what's that? 101.350 equals. Now, I don't remember the density of air exactly, but I remember it's roughly 1 kilogram per. No, it's okay. We'll go with just 1 kilogram per meter cubed. It's roughly 1. I remember that. So the G we also know it's 9.81, and the H is what we're looking for. So if I divide that by 9.81, so that's going to be roughly. It's going to be roughly 10 kilometers, roughly. Now you're only doing this as an estimate. It's not going to be exact. About 10. Now there are some assumptions I'm making which are wrong. Assumption number 1, that the G is 9.81. It's actually only 9.81 here. Later we'll learn as you move up, the gravity force decreases. It's not as strong. Second assumption, that the air is like water and that it sits on the surface, whereas in reality what will happen is there's more air here and it gets less dense as you move up. So it's not like an ocean where there's air and then no air, like water and no water. But it is right to say that it's roughly 10 kilometers, meaning that I invite you to go to 11 kilometers and tell me if you notice if there's any air. You will not notice any air. So really 10 kilometers it's going to be bigger than this. It depends on what you consider to be the limit, because like I said, it decreases. So for me, I'm just talking about the atmosphere we can breathe. I feel like 10 is a good answer. Anything past 10, it's too low density to be, interesting or important. In other words, the safe zone is 10 kilometers. I can't remember. Yeah, and this kind of makes sense because the biggest mountain I think is Mount Everest, which is 10 kilometers. Is that? So when people are at the top, they're really pushing the limit here, and often they have to bring oxygen tanks with them as well. So 10 does seem like a reasonable limit here for the atmosphere. After that, then you start to notice it really quickly disappears. Yeah. So this is how you could make it more difficult. Now, this isn't really a real exam question. What I wanted you to see that with some simple formulas and with some simple facts like the pressure at the surface, you could calculate something not so simple, like how big is the atmosphere. Yeah. Okay, so when Lucia, always so quick to leave my class. It hurts my feelings. Okay, so here's some for you to try.
We'll do it in the next class.
Well, yeah, because we only have one class now. Oh wait, we have one class later.
Yeah.
Ah, so we could do them in the next class, and then I'll do them on the board. And again, that leaves you with a
Lab.
lab report as homework then. Yeah. Okay.